This is Unit 1, Video 8, and in this video we'll talk about the Bohr's atomic model. We've been discussing electron orbits, and here we're going to go into the specifics of some proposed models that explain how electrons orbit the nucleus. So, Mr. Niels Bohr, here's another dead guy that was instrumental in our understanding of the atom and the electron specifically. And he said that electrons move like planets around the sun in circular orbits at different levels. And this made a lot of sense because when they calculated the relationship between an electron who is negative and a proton who is positive, they found that the positive and the negatives attract each other based on a very interesting pattern, which matches the same pattern as the planets going around the sun. So this was actually a very good logical leap. It turned out to be wrong, but it was a good first approximation, first understanding, and this concept is still actually used today just to understand or to explain the elementary side of electron orbits. But we will talk about Bohr's atom first. So, amounts of energy will separate one level from another, and the higher you are away from the nucleus, the more energy you have. So if you're further away, like this electron has more energy, the closer you are, the lower the energy you have. Now, it's really important to understand that there are no in-between energy levels. There's no such thing. An electron, for example, cannot exist in this region. It can only exist at this level, and then it can exist at this level. And actually, it can jump between the two levels, but it cannot orbit here. An electron is not allowed to orbit here, which is not the way the solar system works. The planet can actually orbit anywhere it wants. If it were to slow down, then it would, go between the two orbits. So if it speeds up, it'll go. So this is not restricted to planetary orbits, but it is for electron orbits. And that's what we call the levels to be quantized. They are specific energy levels. A good example of this is a ladder. You can't step between the ladder. You can only step on these rungs. And that's essentially how it works for any atom. You have certain energy levels the electrons are restricted to. Now, the levels are actually given right here, levels 1 through 4. The first level can hold 2 electrons. The second level can hold 8, the third 18, and the fourth 32. And this follows a very simple equation. You take the energy level, which is n, you square it, and then you multiply by 2. Now, this is pretty amazing because this is a really simple equation, but it describes the relationship or the properties of electrons at the atomic level, the behavior of and how many electrons there are. So very simple, you take the 3, you square it to give you 9, you multiply by 2 to get you 18. Really simple equation, very elegant equation. It tells you how many electrons can fit into each energy level. So we can now draw the Bohr model for any element. So if we do the element silicon, and silicon on the periodic table, if you take a look, is element number 14, which means it has 14 electrons. So really, for the Bohr model, we just need to draw 14 electrons. Because silicon has 14 electrons, it also has 14 protons, so you can put plus 14 in the nucleus. There's no need to really draw out the nucleus and its particles, just put plus 14 will work. And then we'll put a few energy levels around silicon. Now the question is, how many energy levels do we place around silicon? Well, in this case, we'll need 3 energy levels. That's because the first energy level houses 2 electrons, the second one houses 8, and the third one we saw houses 18. We need a total of 14, which gets us into the third energy level. So the first one has 2. You'll see me place the electrons kind of on opposite sides. The second one has 8. I'll go ahead and put them on opposite sides here as well. That's 4, 5, 6, 7, 8. So notice what I'm doing is I'm spreading the electrons around to kind of signify that they repel each other. They don't want to be close to one another. That gets us a total of 10, and I just need 4 more. So 1, 2, 3, 4. So really simple model, but this is the electron Bohr model for the element silicon. I take a minute to draw one for fluorine in a similar manner, and keep going. Now, the next model that we'll look at, actually given to us by Mr. Schrödinger, which treated electrons as waves, is the quantum atomic model. So where Bohr said that the electrons exist in these orbits, based on Schrödinger's model, we now call them orbitals. So we actually kept the same idea of orbit to honor Mr. Bohr, but now we're going to talk about orbitals. And here are what orbitals look like. This is the real picture of an atom. So the electrons actually exist, as you'll see, in these three-dimensional orbitals. And it's not nice clean waves, not waves, I'm sorry, but nice clean orbits, but it's more three-dimensional areas around the nucleus. Here is the nucleus of the atom, still right in the middle. So really a different picture than what we initially thought. So an orbital is a three-dimensional region around the nucleus where the electron can be found. And so we have two orbitals that we're showing you here. The s orbital is actually going to be spherical. This one looks most like an orbit, but it's not two dimensions, it's actually in three dimensions. So the electron can actually go anywhere, throughout the atom, forward, backward, around it, around the nucleus. A p orbital actually looks different than an s orbital. It has this 8 shape, sometimes called a dumbbell shaped, and there are actually 3 dimensions. So there's 3 types of these p orbitals, as you'll see. And atoms have different energy levels. So this was true. Bohr was correct in saying that they have different energy levels. Sometimes we'll call these shells, energy shells. And the idea of a shell gives you more of a 3-dimensional understanding. A shell, is all around the nucleus. So shells is a good way of thinking about it. And we use the symbol N to designate energy levels or shells. So here we'll increase in energy as we come away from the nucleus. Remember, the nucleus is somewhere down here. Shells then are further subdivided into subshells or sublevels, levels into sublevels, shells into subshells. And then we use the letter L, and this is actually cursive L, and to label these sublevels. And they have a letter designation, the S, the P, the D, the F, and these are the 4 most important subshells that we'll look at. From here on out, you go into the G, H, I, J, and just keep going down the alphabet rather. But we will not get to these. These are going to be really far out, and no electrons will exist in them essentially, even though you'll see that these sublevels are possible. The sublevels then are broken down further into, well, before we talk about that, here it says that the number of sublevels is related to the shell number. So for example, if you have shell 3, it has 3 subshells. The first 3, S, P, and D. And here there's an equation that says there are n-1 number of subshells in a shell. So if your n is 3, then n-1 means you go from 0 to 1 to 2. That's really how it works. It's a bit confusing. We're not going to do too much with this equation, but that's how you determine that. Subshells then, here we are subdivided into orbitals. The orbitals is what we come to. That's what we want to understand, how the electrons behave. And here are the number of orbitals in a subshell. The S subshell has only 1 orbital. The P subshell has 3, the D has 5, the F has 7. You can see a pattern. You just add 2 more each time you go up. And the way, there's an equation for this as well. We're not going to use this, but these are designated from negative L to positive L. So if you have, for example, the P orbital, which is designated with the number 1 for its subshell, what you do is you go from negative 1 to 0 to positive 1. So you end up with 3 orbitals for the subshell. Again, don't worry too much about understanding this, how it works, but more importantly, to understand the how many of each. Here are, once again, the designations. This is your S orbital. Notice it's spherical. Think of S for spherical. And there are 3 p orbitals. Now, each one goes in a different direction of the 3-dimensional axis. This is the x direction. This is the z direction, and this is the y direction. Usually we think of this as the y, but they kind of flipped it here. Now, these orbitals, this is the p orbitals, combine together then to give you this subshell. So the whole subshell is composed of the 3 orbitals, and that's really how it works. Let's show you a few of the d orbitals. There are actually 5 d orbitals, and they look a bit interesting. Four of them look like a butterfly with four wings, and they're oriented in four different directions. The fifth one looks really strange. It's like a donut shaped in the middle, and then kind of like a p orbital below and above. This idea of the 8. All 5 of these put together give you the subshell. So this is the D subshell. Pretty complex, and you would actually have to use just computer models or graphing programs to be able to see this or to be able to graph this. But the D subshell is pretty complex. And so the F subshell with its F orbitals are even more crazy. So this is like the nucleus, and around the nucleus you have now 8 lobes. They just get more and more strange, and we're not going to study the F too much. And then beyond the F, there's really not much to talk about in terms of actual elements. So here is the final level of these electrons. Electrons can have either a positive or a negative spin. This is kind of the last designation of an electron. And each orbital can have a total of 2 electrons with opposite spins. This is really important because an S subshell then, which holds 2 electrons, the P subshell, which has 3 orbitals, each with 2 electrons, give you a total of 6, and the D subshell holds 10 electrons because it has 5 orbitals, each having 2 electrons. Now we're going to show you this on the periodic table. This idea actually is seen visually on the periodic table, which is really neat. So last thing to say about these spins, these are essentially the specific energy states of electrons. Oftentimes we'll use an up arrow for an up spin and down arrow for a down spin for electrons, to designate electrons. So here really is the whole summary of the quantum model. If you take a look at any shell, let's actually take a look at the third shell. The third shell has 3 subshells. Notice the S, the P, and the D, 3 subshells. The S subshell, we said, has 1 orbital, the P has 3 orbitals, the D has 5 orbitals. And because each of these hold 2 electrons, you have 1 times 2 electrons, 3 times 2 is 6 electrons, and 5 times 2 is 10 electrons, for a total of 10 plus 6 plus 2, a total of 18 electrons. And you can analyze every level, energy level. For example, the 4th energy level having 4 subshells with these numbers of orbitals for a total of 34 electrons. Remember, initially we gave you the number of electrons as 2n squared. So if you do 4 squared, it gives you 16, times 2 gives you 32. So this is actually all lines up. That's all put together. This is a good summary. Study this and make sure you understand the difference between the orbitals, subshells, and electrons. And we'll actually do much more of this when we talk about electron configuration. So here's a quick practice problem for you to try based on what we've talked about, and this completes the lesson.